Perfect. So, welcome to the last lecture of Combustion Science. Francesca, please. Because I forgot to mention to you that this is the last lecture. It's not the last time that you have a slot dedicated to this, but the last slot will be Franz preparing you for the exam with numerical questions and theory questions that he might have prepared or that you might want him to prepare. So it's an opportunity for you to send him an email. Okay? But lecture-wise, this is going to be the last time. And as we agree, it is going to be a special lecture. It's not going to be part of the exam, but hopefully that will not explain why a quarter of the room is empty. But hopefully you can enjoy it. It's a topic that it was not part of the course before, and if this lecture goes well, maybe it will be part of the course in the future, and then it will be part of the exam, which is an introduction to fire dynamics. This topic, it is not in the book, so, well, it's not going to be part of the exam. But if you want to read through it, it will have to be the slides, which act as notes. The authors of the book, which are doing the second edition, are actually planning to put a chapter on fire dynamics. They might have things in common to what you are about to see, but there will be variations probably. So the objective is to tell you, a specific lecture group, which mostly are mechanical engineers with some chemical engineers and some material scientists, which I don't know if they're here today. You're one of them, right? So one material scientist and no more material scientists? Any chemical engineer? They left, all of them. Okay. Well, so you see, mechanical engineers and a guest. And a structural engineer. Francesca is a structural engineer. Oh, yeah, between. Good. I assume already a substantial knowledge in combustion. I will not call it advanced combustion, but obviously I'm not going to be stopping in the details of combustion or what happens inside the flame. This is actually assuming that and launching you into what you typically don't see in combustion course, which is fire dynamics, the uncontrolled combustion. And that we will take you little by little into the process of the fire, putting at the end an emphasis into how the fire evolves, fire growth, and how it behaves inside a compartment. A compartment being like a room. So just to know, you will see there is a significant influence in my understanding of fire dynamics from this book. This is an absolutely gorgeous book by Professor Dougal Drysdale, a professor in Edinburgh. Edinburgh and Professor Dougal Drysdale are very intimately related to the birth of fire science as a discipline. A discipline of scientific discipline cannot be called a scientific discipline, no matter that some people might want it, until you have a textbook. Not a book. Not a book, a textbook, which means it's a book that you can actually teach from. Not to PhD students, because they can go through anything, but actually to precisely the level where you are, and even younger. Some of you are in the master's degree or finishing your MNG, but actually this book can actually, in Edinburgh, for example, we use it to teach also undergrads. So thanks to him, we have a discipline, right? So he has a point, which is very important. I want to illustrate about the multidisciplinarity, the extreme multidisciplinarity of fire dynamics. Fire dynamics is the science, the phenomena that we study using scientific methods that are the foundations of fire engineer or fire safety engineer. These are the engineers who, day and night, every day of the week, without a break, are actually making sure that we, not just us, but actually the rest of the world, are safe from fire at all times, no matter where you are. And when they fail, it becomes very obvious. But when they don't fail, it doesn't become obvious. So it's a type of profession that is very, very frequently forgotten, and we only miss them when they have a very specific types of failures. Some failures are really bad, okay? As everybody is thinking probably of Grenfell. So those are the fire dynamics. What I'm going to be seeing today is the foundation. In the same way, not dissimilar, as thermodynamics is the foundation to mechanical engineering, structural mechanics could be said to be the foundations of civil engineering, and chemical kinetics could be the foundations of chemical engineers. Obviously, they see way more than we think chemical engineers see more than chemical kinetics. I am convinced that civil engineers see more than structural mechanics, and we know that mechanical engineers see way more than thermodynamics. But these are the core substances that actually in reality gave birth to the disciplines. The same way that fire dynamics is the foundation of fire science, of fire safety engineering. But fire dynamics includes a significant amount of thermodynamics, a significant amount of chemical kinetics, and a significant amount of structural mechanics. And that explains that for fire safety engineering as a discipline and a science, to evolve, everybody has to evolve. Or we are as immature as the most immature of all of them. so to speak, right? And we cannot be as fast as the fastest that we wish. We're actually as slow as the slowest. That's just to bring the disciplinarity of the phenomena. And this is from Dougal Drysdale. So when we think of fire phenomena, very often, the first time that you are thinking of fire phenomena is a very informal exposure that you had to this. Not like some people, we've been looking into this for many years. So it's important that everybody focus a little bit on what we think. There are a lot of fire phenomena. Now, probably, even in the UK, a place where there are not many wildfires, but what is happening in California, which is absolutely ridiculously catastrophic, or what happens every single summer in the Mediterranean, or has happened in the North Europe, and it happens in Sub-Saharan Africa pretty much every week, is forest fires, which is invented by nature, discovered by humans, and it led to civilization. But that's not the only one. Actually, chemical engineers, they are very fully aware of when things go wrong in their plants. These are very dangerous systems. Fires are never small. When there is an accident that is not stopped, they end up with big industrial fires. They take into account that they deal with oil, and they deal with all these weird chemicals, and most of them are flammable, explosive, or very scary. Also, the fires happening in buildings. If you think of Grenfell, this is actually where our discipline spends most of the time, scientifically speaking as well. So because each of these disciplines will have a different fuel and a different set of dynamics. And I'm going to bring you little by little into the one of what happens when the fire is inside a building. It behaves completely different if it's polymers. Think of this room burning. Completely different of how the fire will behave, it will be initiated, how the flames will spread, how the smoke will behave, how it could be suppressed, or how people could evacuate in a building that if you are in a chemical plant or if you are in the forest, completely different. But the science, the laws of nature that control the phenomena are the same, okay? But we know very little about them. And just to highlight, when we talk about buildings and safety, although I could replace this slide now with Grenfell, is in 2001, the Twin Towers, actually not just those 2 towers, but 5 towers, high-rise buildings in the middle of Manhattan because of the terrorist attacks that happened, collapsed, the 5 of them. 2 of them because of direct hit from airplanes, although we know that it was not the airplanes that brought down the towers. No matter that Bin Laden was a civil engineer, he was not thinking of this. It was actually the fires that were produced by the airplanes that actually brought those 2 towers down, and 3 more that were not hit by the airplanes. It's an event now probably is forgotten. I really wonder where were you in 2001? Where were you? So was this? I was starting my PhD. Where were you? What were you doing? You were 4 years old. Wow. I'm old. Wow. Okay. So yeah, in 4 more years, the generation were not born when this happened. Wow, I'm old. Okay, good. So our generation, everybody knows perfectly what you were doing precisely when this happened. It's just because he literally froze the whole planet, Earth, literally. It was on TV and everything. But now we are kind of forgetting about it. It changed our field significantly, especially our field with structural engineers, because this is a structural problem. And in a similar way as Grenfell, it is changing the way facades are being built and how fire service actually fights fires, because in this case, there is no excuse of a terrorist attack. I should update the slides. But not just these specific events that are very scary or that might happen or not happen with some frequency, but a few years ago we realized that society as a general, because especially in civilization in countries where not many people, always relative time because of fire, there's a tendency to forget that that all our environments are flammable. And we have multiple ignition sources all around. And when they mix together, things can go really ugly. So we went into a database of people have spent an incredible amount of time going through newspapers and reliable media to recover information on technological disasters. And they cover 110 years. So we did a study in 2010. Okay, and they started this database from the 1900s. So these are disasters that actually were shared with the other people, okay? Technological. So this was not earthquakes, this was not lightning strikes, forest fires will not be considered technological. This is humans doing something, typically industrial and typical engineers, that goes wrong, okay? And it goes really bad, actually. And we can actually assess the number of how bad it is by the number of fatalities immediately after. This is important. It's a proxy to the badness, to the how bad or the onerous of the event. How many people die immediately after of the event? Not how many got injured, not what is the loss, or how many people die 3 months later because it was like a nuclear leak, for example. And then you put it together, and then you can classify that based on chemical leaks, collapse, being a crash in a rail or in air, or water, like a ship collapses and people, okay? So if you are in a ship and the ship goes down, it is considered a technological disaster because nature did not invent ships. It was an engineering invention. And there is one in particular we're very interested in, is fire explosion. When we put all this together and we went to the database, we interrogated the database, we actually discovered that is this, you put them in order in rank, okay? Some of them are very negligible, what has happened in the last 100 years, and some of them are absolutely massive. This one is fire. So it's not just that fire scientists are saying that fire is bad, and you will remember about our words when the fire hits you, is that actually humanity, since the dawn of humanity, has been suffering from fire. But some countries are much safer, and some other countries are not, which is quite interesting, that the immediate number of fatalities because of technological disasters actually are led by fire. If you were to be looking deeper into this database, which we did, you will see that a significant fraction of this was fires and explosions happening in coal mines, which is very scary to think what the Industrial Revolution and the steam era actually brought in terms of casualties that probably not many people die. All the amount of miners that were dying in these events is absolutely horrible. If it happens now, I mean, people will definitely be having human rights courts on this. But then engineers not just record when fatalities have happened, they actually try to learn from every single one of these disasters to make things better, and sometimes actually engineers do it without having to wait for the disaster. And if you put everything together, there is a very successful story of how engineers have been protecting citizens from fire continuously, year after year. There are 2 databases that can be relied on, only 2. The rest of the world, everybody has fires, but very few people actually does a consistently good job collecting data. And these 2 are the 2 Anglo-Saxon countries, the 2 leading the US and the UK. The US absolutely massive, big database covering geographic locations and different subcultures, and the UK a much smaller one, okay? But the 2 of them have amazing databases. For example, if you plot the American one, you look into the amount of people who have died because of fire per population, so this accounts for the growth of the country, of the shrink, over the last 100 years, and you see a steady, obviously goes up and down, with fashions, with big disasters, a year that everybody was paying attention, a year that no one was paying attention. You see an absolutely success story of, over the last 100 years, a 90% reduction in the fatalities. It will never go to 0, and about 20 years ago, we entered a phase where people could actually forget about it. There were so few people dying because of fires that actually they started to forget about it. Whereas at the beginning, even before we collected data, the number of people dying in fire was so large, it was actually considered an act of God. It was, you probably are familiar with this type of thinking. It's like, oh, we did something bad, and we deserve what happened. And obviously, humans cannot interfere with an act of God. So fire is just that you sin, and that's it. And engineers, what are you doing here protecting us from an act of God? That's okay. And that kind of mentality, which the Romans, for example, had that mentality when there was a fire in the city of Rome. It was like, obviously, no, you guys are not behaving well. You're not going to a temple to pray often enough. And this is what happened. You just lost the city. Let's just keep the city exactly how it was before, doing exactly the same things, but please go to a temple more often. It was kind of that kind of behavior. If you look into the number of injury-related deaths, which are not dying for natural circumstances or dying because of a sickness in the hospital, is injury. Is something that has happened to your body, something external happened bad to the body that has happened, an injury. And you look this worldwide, you see 5% of injury-related deaths are because of fire. 5% is significant, but how that significant is to something else. Think of injury-related people in war. Most people in war, when they die, being in the front or in the homes, it's actually because of injury-related, and that's 2%. So it's actually more than twice the number of deaths because of war in the planet Earth. Most of these people, about 80% of these 5%, are in low to medium income countries. So this is not happening in the UK. This is not happening in the US. This is not happening in Europe. This is happening in the rest of the world, actually. The media is not as mature, the engineering communities are not as mature, the governments maybe are not as mature, and these things happen a little bit in a hidden environment. But although the US, Europe, are much better at protecting the life of the citizens, much better, although relative, it has a tremendous cost. The amount of money that it is invested in protecting citizens is massive. Let's look into the UK case. The current number of deaths that are expected, is just out of the statistics looking into what is happening in the last 10 years, is about 320 people. This is pre-Grenfell. Grenfell is an anomaly. It increases this number by 50% in one single event. But hoping that Grenfell is not going to be happening every year, this is about the amount of people that die. This is the number of people that die in the UK, also because of drowning or because of asthma. This is the people, no? You are not worried about a crisis of asthma attacks or a crisis of people drowning, no matter the countries in Ireland. But this is the number of people that die in a fire. Now, what about the people who get injured in a fire? They don't die, but they get injured. They might actually get injured for a really long time, and maybe their lives will be completely changed because of the scars of fire burns. Or the number of buildings have been lost. Or the material, literally, the material that has been lost. Or the businesses that were not able to operate because of fire. So the tunnel was closed, because the building disappeared, because their hotel was gone into flames. So when you look into that, that's the direct cost. So direct cost is 2 billion to the economy of the UK. The indirect cost, which mostly is the fire service. There is not one town in the world, or town going into, I don't know what would be, village, it's too small, but something that is town, a little big town, that doesn't have a fire service. Any place in the world, unless it's an informal settlement or a slum or something like this, which obviously has an organization. Because everybody knows that fires can happen and you have to protect people. And these people, all of them have an engine with water, with helmets, prepared to actually enter the fire and rescue, literally. Or it's like, if you were to be an alien, coming from a planet that is not flammable, because it's not like there's no oxygen or something like this, and you arrive to the planet Earth, they will be like, this really funny. They all have their kings and their presidents and their leaders, and they also have these guys, our fire service guys all around. Okay? Every single one. And day and night, these are professionals. They need training. They need maintenance. They need equipment, very expensive equipment. The city of London have actually thousands of them around, and that's a cost. That's an indirect cost. So what we have learned is that to protect our fire, you either put the money in protecting them, and a significant amount of money, or you don't put the money, but then you suffer the consequences in not maybe money, also in money, but actually in terms of life. And governments have the ability to make that choice, or at least maybe they're trapped in one or the other. It's always expensive to fight fire, so it's far from being gone. What does the engineer do? Well, the engineer tries to understand fire in order to stop it, but it can stop the fire or the consequences of fire in many places. These are what are called the layers of protection. There are many layers of protection. I'm sure there is someone that thinks there are like 15 or 26. I think I saw recently a book that says like 26, and I don't want to bore you with 26 layers. But I condensed these. Dougal helped me tremendously, Professor Dougal Drysdale, with his 8 layers. But I think I can condense it even more to 6 layers, but I cannot be condensed anymore. Okay? And these are the layers. The first one, and this is order of chronology, and probably in order of importance as well. Okay, although it's a little bit controversial. The first one is to prevent. Don't let the fire happen. You are sitting on flammable chairs. Please don't bring the lighter. Please don't play with matches on them. Please don't leave your lithium-ion batteries on it when you are not around, or don't leave a source with high voltage wire next to it, because then you will be making sure that actually a flammable material and an ignition source meet together. Or if you're going to do it, let the fuel not be too flammable, which means have a polymer that is not just ridiculously flammable like it would happen with polyurethane foam, and don't let the ignition source to be absolutely largely or energetic, right? Just let it be mild or something like this. If you fail at the prevention, then you have to detect as soon as possible. Here in the UK, we pretty much everywhere where we are, even in our private homes, we have detection. Detection is a very simple technology, extremely simple and expensive and very reliable. And some of you are thinking, what about false alarms? Yeah, that's true. It's not perfect. It does have consequences, negative consequences, when someone is playing with it, or when it actually decides that the dust is actually smoke. But it has saved so many lives for the few pounds that it costs. That is officially the best technology in saving people from fire. The third one is, what do you do with that detection signal? So you hear the signal. Imagine that it's not a false alarm. It's truly a fire. What do you do with it? the first thing that you do really is you order evacuation, or you start to evacuate. You start to take people away from the fire, because the fire really doesn't do anything positive to people. And the faster and the better. The fourth one is compartmentation. This is a big thing in the UK. It's a big thing in Europe, but a big thing in the UK. Compartmentation. You have seen many doors that says, the sticker, the universal UK sticker of fire door. And we have a lot of fire doors. So when a North American comes into the UK, they laugh about this, in particular hotels, because there are so many doors in the UK, and all of them are super heavy because they are fire doors, right? This is very important. This is compartmentation, which is if I'm going to fail, well, if we are going to fail preventing the fire, and hopefully we have detected and people are evacuating, we must keep the fire in what is called the room of origin. Okay? So don't let the sickness spread, because actually that's when you lose control. And an extreme case of this is Grenfell. It was not just getting out of the room of origin, it was getting out of the flat of origin, it was going actually out of the story of origin, and it was actually even going vertical, which is not even considered in the strategy to defend the tower. And the UK is very strong on compartmentation. Every country it is, but the UK more. That's what is called passive, because the door is always there, and the door doesn't have to do anything that day that it's not doing right now. It's passive protection. Compare that to suppression, the fifth. Okay. We're thinking of sprinklers. We don't have sprinklers in the UK, not many. Sometimes I speak in places where they are, and not here. These are the sprinklers. It's a beautiful technology. It's a glass valve with a gas. If it heats up, the overpressure breaks the glass, and the glass happens to be the valve to the water supply, a specific water supply that is separated from the rest of the building. And then it rains. It literally rains in the room. And if the glass had activated because it was hot, chances are very high that the fire is not very far. So you are like closing your eyes and thinking, hopefully the fire is there. Okay? And sprinklers are very, very, very reliable. The technology is inexpensive, the activation itself, but it requires a system of its own. It requires water supply of its own. And the most important thing is, you install this system, has to be ready every second of the life of the building, and it will only be activated maybe once in the lifetime of the system. So as an engineer, you're designing this massive system going all over the high-rise building, massive pumps, specific pumps for it, with a specific engine for it, with a different energy supply, and actually even an automatic supply of energy, just for it to be activated one day, and hoping that that day really it will be ready, nothing will have been broken, the water will be with pressure, the pumps will be there. Okay? So it's a very, as an engineer, I get the tension of the suppression layer, right? It's very tense, it's very tiring. Whereas the passive one is like, well, I'm just here anyway. Right? The UK is very strong on compartmentation. The Americans are very strong on suppression. The two of them have ended up with buildings that are much safer than the rest of the world, but by combining different layers. As an example of, you don't have to address all the layers, but you have to consider all the layers and combine them in the flavor of the time. The firefighters, you will consider the firefighters is not a layer. I've been told about that. Firefighters could be considered suppressions. A different type of suppression is then connecting to the mains or to the truck, and it's actually helping in the evacuation. These are the two things that the fire service does. It suppresses or helps in the evacuation. It could be, for example, someone got trapped. That's an extremely long, difficult evacuation. The firefighters will actually make sure that they complete that evacuation by taking even the people who cannot evacuate by themselves. And the last one is structural resilience, which means that the tower, the building, should not collapse. Or at least it should not collapse for sure when there is residents inside. That is actually literally criminal if it happens. Or, and that's more complicated, if the firefighters have entered into the building for rescue or for suppression, it should not fall on them. Okay, think of what happened in the World Trade Center, which definitely the towers did not sustain the fires. There was people still inside because they could actually not evacuate from where the airplanes hit. And above, these people could not evacuate because the airplanes actually had cut the stairs. People below could evacuate, but the firefighters were up to fight the fire, walking, 45 minutes walk, and it collapsed with 300 of them inside. So that's a layer that works. Now, going back to Grenfell, I am assuming this is Grenfell over here, that you are all familiar with what happened, more or less, what happened here 2 years ago. We'll not go into the details, but in Grenfell, of these 6 layers, 5 were breached by the fire, by the circumstances. So only 1 layer was not breached. Do you know which one? Well, yeah, some of you definitely know. So raise your hand if you don't know which layer was not breached in Grenfell. So definitely the prevention failed. Definitely there was a fire. The detection failed because although the people in the flats actually were able to escape and they actually told a few neighbors, there were hundreds of residents in the tower who didn't know there was a fire going on until much later. Detection didn't work. Evacuation didn't work at all because the evacuation was extremely slow. It actually didn't happen. It was actually voluntary instead of mandated. Some people, when they wanted to evacuate, it was too late. They could not evacuate. Their path of evacuation was actually compromised by the fire. They could not evacuate. It's pretty bad. Compartmentation definitely failed. That's the number one layer that was breached. The fire was going left and right pretty much at high speed. Suppression completely failed. There was no sprinklers, and the fire service could not go above 18 meters. And from the inside, they were in rescue. They were not in suppression. The tower did not collapse. That's the only thing that worked in Grenfell. And I tell you this because the firefighters, when they were in Grenfell that night, they were thinking of the World Trade Center. They were thinking, this fire is absolutely horrific. We have to enter to rescue people. What if the tower collapses? This tower, in reality, should have collapsed. In terms of when it was designed, the structural engineer who designed the tower was never asked, not even in the wildest dreams of authorities, to sustain an absolutely horrible fire as we saw. This actually is what is called burnout. That tower was burning for 24 hours. There was literally no gram of polymer material or flammable material that was not burned in that building. It was an absolute disaster, an inferno situation. No concrete structure has ever been requested to sustain like this, not even a military infrastructure. And the tower did not collapse because of the resilience, because of the redundancy, because the safety factor of the engineer thought it was 2, but probably was 22. That's the only thing. So the tower should have collapsed according to design, but it did not collapse. Okay? Which is fascinating of engineering in a way, now detaching ourselves from the strategy, that is actually when the things that should have worked did not work, and the thing that no one asked it to work actually worked. But I want you to see the importance of fire dynamics as a race to save people. This is a plot where you see time here happening, things are happening, the events are evolving, and this is how complete is the process, different processes. In red is the fire. So the fire has an ignition, that's where everything started. The fire at the beginning goes slowly, the fire starts to accelerate. Then it's something that we're going to discuss later on, which is called flashover, when actually the fire engulfs the whole of the room of origin. It cannot literally be bigger than the size it has reached, conserving the loss without breaching the laws of nature. And then actually might go to different rooms or might different stories. Okay, so you have it breaches the room of origin. Compartmentation has failed. Suppression has failed. It might actually go beyond the floor of origin, and actually is about to be engulfed in the whole of the building. If we let it breach here at this time, the whole building is compromised. And then at the same time, you have to evacuate people so they don't get in the path of the fire. So the people in the room of origin, they need to evacuate before the whole room becomes involved. And the people who are evacuating the floor, they need to fully evacuate the floor before the whole floor gets involved. So it's like a race between the blue, which better be very fast, and the red, which better be very slow. Okay? And at the end, what you have is you need to evacuate the whole building before the whole fire is involved, or before, this is when the structural engineers come in, there are 2 of them today with us, is the black line, is when the structure starts to collapse. So it's not just that the whole fire is in fire, actually it might be that the tower starts to collapse even before the whole fire has involved the building, because there is what is called the partial collapse. Okay? And before that happens, you have to evacuate people, and hopefully firefighters are somehow aware of this and they have not started to enter the building and put the lives on risk. I want to show you this video. It's a classic. It was actually filmed in VRE, which is not far from here. It's in Watford. It's just the north of London. You can see by the style that is totally 70s. The sofa, the way the scientist was dressed, the doll. I mean, everything is fantastic. It's definitely the 70s. It's an experiment in the 70s. It's a room. It's a mock-up room. It's not a real room, but it's actually furnished in a way that perfectly equates to a room of that time. And it's missing one wall. So it doesn't have 4 walls and ceiling and ground. One wall has been removed, so you have visual access. That changes the dynamics, but it gives you beautiful access to these diagrams. So we have seen an engineer has arrived, has ignited the sofa. The sofa is the most scary part of what we have in our houses because it's relatively easy to ignite, and it has an incredible amount of fuel. So when a sofa or a mattress ignites, everybody worries. Okay? When a little chair or a little curtain ignites, the fire will have a different type of speed. But they went into the sofa knowing that that's the most vulnerable part of a compartment. And you can see the flame develops, you can see the smoke, you can see that it's actually spreading first vertically and actually starting to burn different parts of the sofa. And that's a minute after the ignition. You can see the smoke starts to accumulate at the top. You can see it over here perfectly. It creates what is called the smoke layer. Actually, the smoke is like an inverse bath. You're filling up the bath. When you're going for a bath, well, this is the opposite. The smoke actually starts to fill the top. And when it starts to find windows or doors, it starts to move to different compartments. And the pump, the source of this fluid is the fire itself. You can see the significant increase in flame length, which already tells you the amount of fuel that is involved in this burning. The fire continues growing. I'm going to accelerate it for the sake of time. You can all go and click. Now the whole sofa is engulfed in fires. You can see it has created its own wind now. It's not just at the mercy of the external conditions. By the sound, you see that it's actually able to break windows because of the heat, and it starts to modify the inflow of oxygen that is needed for the burning and the outflow of the smoke. And you can see how the fire is evolving. It starts to burn all horizontal surfaces. The carpet is paralyzing. It's so hot, the carpet has ignited. And now you have reached what is called flashover, which is pretty much this fire could not physically be any bigger than what you see right now, because everything that can burn is burning to the point that actually is running out of oxygen and actually has gone outside the compartment to continue burning because there is more oxygen inside. Outside. Yeah, that's the process of flashover. Flashover is a name that we use very often in fire science. That is a name that was given by the firefighters. The firefighters encountering that they were going into these fires, and if they were not fast enough...
When body pain strikes, we don't always know what to do. Body pain can be caused by...
Okay. Firefighters finding this phenomena that actually literally impede them to go any farther into a room. No one can enter it. No, it's not that you don't want, it's that no one can enter, not even firefighting robots, in a room that is in flashover. It's actually worse than a furnace. So this is just the images extracted. Okay. So now, the video that I show you from VRA is actually what we try to understand. Why did the fire evolve the way we just saw? Obviously, you know something about combustion, you know something about premix flames and chemical kinetics and diffusion flames and laminar and turbulent. In fire, we are always talking about diffusion flames, which are very large, and all of them are turbulent. This is what we're looking for. The fuel is not in the gas phase. Well, the fuel is at some point in the gas phase, but the fuel is in the solid phase. In buildings, it's solid phase. If it's an industrial fire, some of the fuels might be in the liquid phase. But in buildings, it's solid phase. Polymers and wood, which is also a polymer. It's just that it's a natural polymer, not a synthetic polymer. So we have already seen many of these topics in the course, but not at the size, this significant size, okay, or the type of uncontrolled flames that we see in fire. So if you have a slab of a fuel, a polymer, a foam, a solid slab, a piece of wood, of timber, initially, if in normal life, it's just at room temperature across its depth, that's the temperature. But if it's exposed to heat, this being the ignition source on a nearby fire, okay, then the temperature has to increase. It has to increase on the surface, and there is a point where the surface is so hot, it actually starts to chemically degrade. The process of pyrolysis, which we have already seen, where there is a simultaneous change of chemical composition and physical change, and physical phase. So the solid is a particular composition of a polymer, hydrocarbon, in the solid phase, with long chains typically, and it's solid. Undergoes pyrolysis, it becomes gaseous. It's not really a vapor because it's irreversible. It cannot go back into the solid. So it's a gas already, it's a gasify. And it's not the same chemical composition as the solid. In the process of degradation, at the beginning is the short changes, and later on, as the process of pyrolysis continues, it might actually be longer changes. And what it leaves behind is either melt polymer or a char polymer, or nothing. And then this fuel, pyrolysate, is flammable, will mix with air, and at the beginning, before there is a flame or there is a fire, this pyrolysate will mix with air. It will create a flammable mixture. Okay, this flammable mixture will find an ignition source, being a flame, which will act as a pilot, or a hot surface, or the polymer itself is very hot, and it will ignite. Initially, for a very brief period of time, it will be a premix flame. This cloud of pyrolysate mixed with air that is flammable and finds an ignition source, it will be maybe a second of a premix flame. But then this flame we will establish over the surface of the fuel, and it will become a diffusion flame, and the radiation from the flame, especially from the inside, will actually paralyze more fuel that will actually feed into the flame. And now it becomes more like a candle, where the candle itself and the heat from the candle is actually the engine that is providing the gaseous fuel out of the solid fuel. Okay? And then it will be a turbulent diffusion flame for the rest of the process. Turbulent because if you are in fire, you are looking for something that is seriously threatening, not just a little candle. Called the firefighters, there's a little candle in my room. No, these are big rooms. And also because fire very quickly makes the buoyancy, makes turbulence turbulent. Not because of the Reynolds number per se, but actually the instabilities that happen because of buoyancy. And these are typical things that we do when we study this in experiments with different fuels, different polymers at different conditions. We expose them to a radiant amount of heat. There is an irradiation. This is what is called the cone. It's really nice. It has the shape of a cone, literally, truncated cone. But it provides uniform heat flux that you can control. Laura actually does this for her final year project a lot. And it's very nice because then you have a slab of a fuel and you have a controlled surface exposed to a known radiant amount of heat. And then if you track the temperature of this slab of polymer and you look into the surface, you will see that as time passes by in seconds, the temperature of the surface goes up. There is a point where you have the threshold, you have the onset of pyrolysis, which typically will happen around here, 200 Celsius. Then the pyrolysis starts to be produced. And there is a point where actually it ignites. And you literally see a flame. Okay? And the first curve over here is for external irradiation that is actually relatively low, of 12 kilowatts per meter square. Typically, a polymer might ignite, but if you lower it to 11 or to 10, might not be able to ignite, because you will not be able to pass the polymer through the critical temperature or thermal regime that it will ignite. It will just degrade, it will just be damaged by heat, but maybe it will not ignite. But as you increase the heat to 15 kilowatts or to actually 18 kilowatts, what you see is that you ignite faster, right? What is called the time to ignition, which is a very important parameter in fire science. This is a long time to ignition. This is a medium time to ignition. This is a very short time to ignition, okay? Which is already a parameter that we use very often to clarify, to understand the flammability of a material. If you put a material under one set of irradiation and it ignites really fast, you know that material is very flammable. If you put another material and the material takes a really long time to ignite, it still ignites, but it takes a really long time, you know that it's fuel, it's combustible, but it actually is of lower flammability. It just has an inherent resistance that the other material doesn't have to ignite. Okay? It's not just time to ignition. There are many different variables that we have in fire science to understand the flammability of a solid. Until now, I want to highlight this. It's something that we were writing about in the group recently. Flammability as a name, scientific name, was first given to a mixture of gases. Flammability range, no? Upper flammability limit, lower flammability limit. In a gas, everything is simpler and nicer for science because it can actually put more depth into it. When you go to a solid, it complicates tremendously. It's still flammability, but it's just not about the ranges of mixture of the pyrolysis with the air. It's actually much more complex. It's also heat transfer. It's about flame spread. It's about many other different phenomena. Okay. Pyrolysis is a central phenomena in the ignition of a solid. So fires and pyrolysis very, very closely related to each other, unless you are in a chemical plant where the fuel is already in the gas phase, which typically will lead not to a fire, but to an explosion and a jet fire afterwards. Or even if it's a liquid fuel, you will still have pyrolysis of the liquid because it will not be a pure liquid. It will be a complex organic liquid, and pyrolysis will still take place at the same time as evaporation. Okay? So you have seen this slide already. The process of pyrolysis is when you go from, in fire in particular, you go from solid to vapor or to gas, okay, in one step, and you have a simultaneous phase change and chemical change, okay? And it's reversible and is endothermic. This is very important. It means that in order for the fuel to go from the solid to the gas, you have, well, not you, externally someone has to provide the heat. It's not an exothermic reaction that has runaway and self-sustaining behavior. This is an endothermic reaction. It doesn't want to happen. It will only happen if you give it extra energy. But all polymers, except very, very, very specific rare cases, all polymers, when they burn, they provide many more times energy that is required to paralyze them. Okay. So in reality, the heat of reaction for pyrolysis is very small compared to the heat of combustion of exactly the same material. And that's why many materials, when you ignite them externally, they themselves can develop the fire and not self-extinguish, because they can actually use a fraction of the heat that is being released by combustion to paralyze the next layer, which then will provide even more heat by combustion, and a fraction of that heat will go into heating up the next layer. I want to show you this video, which I'm very proud of. It was actually done by civil engineers, which I think it adds to the quality of the work, because civil engineers typically don't see pyrolysis. Chemical engineers, for sure, mechanical engineers, only we would again to them. But structural engineers, it's an anomaly that they do into pyrolysis. They did this beautiful experiment, and they videotaped it. It's in the cone heater. Okay, this is a surface. It provides a known uniform and constant, known and controllable amount of energy by radiation arriving to the flat surface below. And they put here a polymer that is particularly good for science, not very good for engineering. It's called PMMA, polymetal acrylate. It's good for science because its behavior in pyrolysis is simpler, flammable for sure, but simpler. And that's good. Not very good for engineering is because no one uses PMMA, except for the metakinetic chairs with no occurrence of fire, or architects now put them as facades because they like it more than glass. Fine, but it's not dramatic use of the polymer. But we know a lot about how PMMA burns. Not many people are very fascinated by this, but we know a lot. We know very little how wood burns. We know very little about how many other polymers burn. But PMMA we know. Okay? So they took this video where they zoom into the slab of PMMA. It's transparent PMMA in particular, because then you can see visually a little bit of what happens inside. It's accelerated because otherwise you will be here for ages. It's about, I don't know the thickness, but it's about 5 centimeters thick. You can feel the heat from the top. And if you were looking at it, you can actually see that there was a wave that was actually propagating downwards. That's actually the diffraction of the PMMA is changing, the diffraction constant with heat. So actually it's telling you visually where the heat layer or the heating wave is coming. It's coming from the top, going downwards. Also, you can see the little bubbles. This layer over here that has changed its color are little bubbles of PMMA that are undergoing pyrolysis. And PMMA, when it undergoes pyrolysis, it becomes MMA. So poly-MMA, when it breaks down, it just produces MMA, methacrylate. You can see the layer is growing, but also the top layer now is disappearing. That PMMA is literally going away into the lab, into the extraction fume, and outside into the city. And as time goes by, you can see just the process repeats itself. Now the heating wave is about here, and it's still propagating, but it's lower. The bubbling layer is significant, and actually you can see now that the sample has lost its original form, not because it has the form, but actually it's because it has lost, literally, material. Where is the material? It's in the air. That's the material that if there were to be a fire, we do not let the PMMA ignite, because if it ignites, you cannot see any of this. We just paralyze it, okay, without igniting. All that gas that has disappeared will have fed the flame. You can see now accelerated, you have actually about a quarter of the PMMA is gone by literally pyrolysis. Okay? So this is what the fire does. It just does it very messy, and you cannot see what is happening. But when you decouple pyrolysis from the fire, you can actually observe this phenomena. We are very lucky that if you are interested in a specific polymer or if there is material, you might have some information about it. The first thing, if you want to try to predict, to understand the time to ignition, is to know at which temperature, under standard conditions, this polymer will ignite. You have already seen this concept. It's the concept of fire point. It was developed for liquids. You remember that it's a standard. You put the liquid into a cup. You heat up the cup very slowly, and you always pass by a pilot, and the cup starts to paralyze or to evaporate, depending if it's pure or not pure organic. And then when it reaches a flammable layer at the location of the pilot, that ignites. And then you look at the dial, the temperature of the cup at that time, and you know that when the liquid is at that temperature, it can actually sustain above it a flammable mixture. And then you have the flash point. It was the first time you see this, because it's blue. It's a premix flame. It burns, and it's not able to sustain itself. It's not able to go into the diffusion flame. But if you keep heating up, then you see the flash leads to a sustained diffusion flame, and that's called the fire point. In a solid, the flash point and the fire point happen so close to each other, it's almost impossible or meaningless to separate. So we just talk about the fire point. And then you can go into different materials. This is plywood, this is PMMA, okay, this is wallpaper, and it gives you the time to ignition, fire point, extracted at standard conditions. Because if you change the conditions of the experiment or the conditions that you have around the sample, the ignition temperature will change, as it will change in a liquid or it will change in a gas. But it tells you a lot, it allows you to compare or to rank flammability in a different way. Not the time to ignition, but actually the temperature at which it is. For example, which one is the lowest? The lowest is 300. It's a carpet. Good that we put it very far away from most of the fires. Okay. If we were to be doing ceilings out of acrylic, that would be pretty bad. But at least, the last thing that happens, that burns in a fire, the very last thing, is always the carpet, because it's far away from the smoke layer. And the one that has the highest temperature is this one? Yeah. It's actually a foam plastic. Just the temperature. Then the question is, how fast would this foam or this plastic of this PMMA reach that temperature? And that's when the heat transfer, the other subject that I love, it plays a significant role. You will see, for example, that foam, although it ignites at high temperature, it heats up tremendously quickly, okay? Because it actually doesn't have a good thermal diffusivity, doesn't want to share their heat, which means that the surface temperature gets all the heat, and very quickly it reaches not just temperature, it reaches any temperature. Whereas other polymers, they might have a lower ignition temperature, but they actually they conduct the heat very quickly in time, so the surface doesn't get that critical temperature that fast. So thickness of the material matters significantly, and the heat transfer properties of the material severely modify the flammability properties. To the point that something that I could not teach you in heat transfer when you were doing this in second year, but there is a very beautiful analytical theory which actually allows you to calculate the temperature at any point in your slab, and at any point at any time of your slab. You might want to look into the surface or in depth at different times upon this slab being exposed to the heat. Okay, it's a beautiful equation that you cannot see with me in second year, but it's in Cropera. I think most of you have a copy of Cropera that we gave you, and it tells you that the temperature of that time and that position, with respect to the initial temperature that it had, goes linearly with the heat at which it is exposed, the radiation. That's very interesting. It's linear, not quadratic. It's not a square root. It's linear, and then it has an exponential term that depends on space and time, okay, and an earth function to complicate things a little bit that depends on space and the square root of time. Okay. If you're just interested, which is what happens very often, not just what the temperature of any location, but the temperature of the surface, then the expression simplifies tremendously. At x equal to 0, that's the free surface. That's the first point that will ignite in most of the cases. Then the temperature of the surface with respect to the initial temperature, it grows linearly with the heat flux. It grows with the square root of time, which is quite interesting, or actually is proportional to the square root of thermal diffusivity divided by conductivity. Okay. Which is K rho C. So if you have thermal diffusivity, you divide by the conductivity that you put inside the square root as Q squared. Okay, this ratio is K rho C, which is important. It's a specific arrangement of the thermal properties of the material that dictate at which time the solid will reach its ignition temperature at the surface. Okay, it's controlled not by K, rho, and C, but the specific linear rearrangement of K, rho, C multiplying each other. Okay, it's different than any other type of thermal arrangement. To the point that if you solve for this equation of when the surface is going to reach the ignition temperature, you can rearrange the equation and say, well, the time to ignition, which is another flammability parameter, is actually the temperature of ignition, depends on it, respect to the initial temperature to the square, divided by the heat flux at which it is exposed, controlled by K rho C. So different materials will not only have different ignition temperatures, which we saw in the table before, they also will have different flammability based on what K rho C is. But K rho C is tabulated as well. I'll show you later on how K rho C is tabulated. The expression that I showed you before, sorry, I'm going back. This expression, you can plot it analytically or experimentally and the two methods agree, is what is called classical ignition theory. This is the heat flux in your experiment, okay, in kilowatts per meter square. These are absolutely insanely high heat flux. Don't put your hand. This one over here are very high heat flux. Don't put your hand, okay? But these ones over here would not even ignite a polymer. This is time to ignition. So you see there is this red line. This is what is called the critical heat flux. Any heat flux below this would not be able to ignite the polymer. This data is for PMMA. The one that I told you that we don't care much about as engineers, but as scientists we know something about it. So you degrade the polymer, you mistreat the polymer, you are damaging thermally and chemically the polymer, but the polymer will not ignite below the critical. When you are above the critical, it will ignite. The question is, when? So if the heat flux is just above the critical, it will take a really long time to ignite, okay? But it will ignite. But if it actually goes really high heat flux, it will ignite in literally fractions of a second. When you have a fire going, for example, the ignition source, typically, ignition sources, we want to keep them very small. But when the ignition source, because of an accident or on a lack of safety, goes and grows beyond the critical, okay, you will have ignition. Typical ignition events, initiating events of a fire, are in this range, okay? Unless there is a terrorist attack, or actually probably you are in this way. But once the fire starts to develop, as ignition has happened, there is time where the fire has started to develop a smoke layer, has started to preheat the fuel, particularly actually is preheating the fuel that is next to it. You saw in the sofa, there was initially spread upwards. The heat flux that the element of sofa that is next to the flame receives is here. Okay? So you can see flame spread, we're going to see that later on, as a series of consecutive ignition steps. But the ignition heat flux, or the heat flux that leads to ignition, when you have flame spread, is really high, and you actually have ignition within seconds. And if the fire starts to grow, then actually more heat is arriving to the different locations, and then you actually start to have accelerated fire behavior because the time to ignition of the next ignition layer is actually shorter. Okay? And these are experimental dots, and the line that you see black in between, which follows very nicely the curve from many different authors, is the theory that I told you. So it's a very simple heat transfer theory. It doesn't even have much of a combustion or fire within it, and it actually predicts beautifully these experiments of radiation of a polymer. And this depends on these two quantities, which are tabulated in different books. For example, this is from Quinteri's book, where you have the polymers that I showed you before, and I showed you already this column. This is the ignition temperature, and this is the tabulated K rho C of the material. You can also go to Incropera, find some of these materials, and multiply U by hand the K rho C. K by conductivity, rho density, and C of the specific heat. Okay. For example, which one has a high K rho C? That will be this one over here. Okay. That will be PMMA, has a high K rho C. What does it mean that it has a high K rho C? It's that it will take longer to reach its ignition temperature. Which one has a low K rho C? That's a scary one. Look, ridiculous, okay? A low K rho C, it means it will take a very short time to ignite. It actually has 0.03. It's 100 times smaller than the PMMA, okay? And which one is that one? Well, it's a little bit moved, isn't it? Yeah, perfect, the foam, okay? So the foam, if you look into its table, it's like, oh, my foam is fantastic. I'm going to sell it like crazy. Look, I'm going to tell all my customers, my foam is really difficult to ignite. But I'm not going to tell them that the heat transfer of my foam is absolutely crap. Foams are insulating materials. That means they don't want to share their heat. They actually don't want to conduct it away. That means they actually behave particularly bad in fire. Whereas a material that is actually conductive will actually not ignite at the surface because it lets the heat go by. And I'm going to show you this, and then we give you a break. This, everything that I saw before, is for a material that is very thick. It's so thick, it actually behaves as infinite or semi-infinite. Free surface, and the fire or the heat will never be able to see the end of the fuel layer. No? They're really thick. But the other thing is, and the most dangerous ones, are when fuels are very thin. They are so thin that actually is the opposite of semi-infinite. They actually behave as one single temperature. You've seen this in heat transfer. When the period number, okay, which is the heat transfer coefficient times the thickness divided by the conductivity of the material, is very small, typically below 0.1, then you don't have a temperature distribution of the surface one temperature and in depth another one, or another set of distributions. The whole of it is often behaves as one single temperature. And then the equation that you had before simplifies and it morphs into something simpler, where the time to ignition is not K rho C now, it's thickness rho C. So when you have a Biot number that is very small, you have a sample that is very thin. Conductivity is not a driver parameter anymore. It's the thickness of it, linearly. Okay, it's twice as thick, still thin. Well, it will take you twice as long to ignite. Okay, and then it depends on the difference between the ignition temperature and the initial temperature without the square root, without the square. Sorry, it's linearly. Okay, and also depends on the heat flux, inversely proportional, not mediated through a square. So that's for you to know, okay? Good, so I'm gonna stop it here and give you a break. Perfect, it's almost there. Just reminding you that in the video of the VRE that we saw, we have already passed ignition, okay? This flame has established itself, it's actually releasing heat to the nearby surfaces, it actually started to spread a little bit, it has created a column of smoke, and the smoke is accumulating inside the compartment. And I'll give you 10 minutes. Thank you. Good. So this slide is not very important for you, but you know that as the fire becomes bigger, the number one variable that we use to quantify size of the fire is the power of the flame, right? Which will be illustrated as a length and as a burning rate and even as a volume. And the amount of energy that is released is what we call heat release rate, okay? And this is how a 25 kilowatts flame looks like, and this is how a three times bigger flame looks like, okay? I don't have to show you this. They are turbulent. They're luminous because they're diffusion flames. They have a lot of soot inside. And when you see the smoke coming out, it's because the flame has been perturbed by the turbulence, and the soot did not burn through the flame, and it actually ends up being emitted. And the bigger is the flame, the more turbulent it is, the more holes are produced in space and time, the more smoke is able to be released and be accumulated in the room. But you know this. What you might not know is something about sizes. If you think of just orders of magnitude analysis of a match, if you have a match, a little match, what is at its peak moment, the order of magnitude of its power is actually 10 watts. It's short-lived, it only lasts for about 30 seconds, but that's enough actually to light cigarettes or to light the stove in your house or any other uses that you might have for the match. When a soft fire is burning, and that's more serious, especially in residential locations, they might actually start burning because of a match. That happens very often, or a lighter, or a short circuit. But actually the average heat release rate, not even the peak, is about 1 megawatt. That's a serious change, right? This is 100,000, well, it's 10 to the 5 bigger than the match. And actually the size of a medium size wind turbine. Once upon a time, wind turbines could not be 1 megawatt. Now we're actually way beyond 1 megawatt. But that's a significant amount of power that when it happens in a fire, no one is making any use of. This is a typical approach of an engineer to fire. They're like, this is pretty bad, it's horrible, I'm going to protect people. It's like, oops, I could use that as heat for something, right? I mean, there's so many people that could do power with it. But that's not the end of the scale. Actually, when a room, depending on the size, obviously, and the amount of fuel that it has, but we're talking about typical rooms, not just the massive lobby of an airport, but about this size of the room. When they start to develop to flashover, we're talking about peaks of heat release rate that go into 3 to 10 megawatts. Or when we're talking about a car is burning, a car has a lot of flammable material inside, not just the fuel itself, diesel or gasoline, but actually there is a significant amount of polymers that are always increasing in a car. Now there are cars which are pretty much made of polymer and a little bit of aluminum, whereas the cars that happened about 20 years ago had a significant part of metal. You can actually see this. 2 years ago, there was these big fires in Portugal, and several fires where people that were trying to evacuate in these forest fires were actually trapped in the fire and people died. But the cars actually burned, and you can see the photos of what was left behind, and you can see the chassis. The chassis without any paint, completely white because of the high heat, and there's absolutely nothing left. The aluminum has melted. It's just literally the steel. Only the steel was able to sustain those high temperatures. Everything else is gone. It's like it's empty. But if you see a Tesla undergoing a fire, and Teslas have gone under fire, it's a very strange image. There is nothing left. The car is not there. There's nothing. There's a pool of melt polymer on the floor, and that's a Tesla. You're like, where is the Tesla? There. Well, I mean, there and all around us, because it has actually gone into the atmosphere, which is a particular PR image that electric cars hate. That in particular, obviously, is the extreme of negativity. But actually to say, if it burns, it just literally goes in the lungs of everybody else. And then there is the nightmare of fire, literally, which actually happened, is when a heavy goods vehicle, which means a truck full of stuff. We humans, pretty much everything that we put in a truck is flammable. Even fruit. We've learned that even a truck full of fruit, of melons, it actually is extremely flammable. It's biomass, no matter that but it's very moist. Well, the endothermic requirement of latent heat of vaporization of water is nothing compared to what happens when actually a dry melon is burning. A heavy duty vehicles is a serious fire, and actually can have an average heat release rate of 50 megawatts, which is seriously high. And that's actually the average. The peak might actually be in the 80 megawatts. And that's a bad scenario. But then structural engineers get very worried about this, because if one of these is undergoing your tunnel and it catches fire, and that happens with some frequency, your tunnel has to be a little bunker to sustain this and not to break and collapse out of the heat. Or it's going in your bridge, and Francesca is working on this. And it happens to be stopped and it starts to burn next to the central pillar of the bridge or the cables of the bridge or something like this. So it's a scenario that we humans have a lot. All these trucks are coming and going, and things can happen. And that's not one of the largest fires that humans have caused and have witnessed is actually Buncefield in 2005, just before I was arriving to the country. It was the oil depots of Stansted Airport, so it's kerosene depots, all of them, and one of them ignited because of accidental release. The vapor mixed with the air, it found an ignition source, which I think it was the car of the security guard, and then it actually had this detonation, deflagration to explosion. It actually, and then for about a week, the depots were actually burning, and the firefighters of the UK, not just of Buncefield, the UK ran out of foam to find this type of fires. They actually, after Buncefield was suppressed, they actually, all of them had to go back and completely modify the market of foams because all of them have run out of foam. Because when you are burning, when you are fighting an industrial facility with a liquid fuel, you cannot just use water. That will be a complete waste of your time and actually will be even unsafe. You have to use foam, which is, it not only carries the water and takes the heat by being vaporized, but actually creates a layer that avoids the oxygen arriving to the liquid. The foam is what it does, and then it protects it somehow. But when you look into the heat release rate, which we're going to call Q dot, okay, that's the power of the fire. You know this. You can actually extract the heat of combustion or the effective heat of combustion of your polymer, and you know how to do that based on the chemistry and the stoichiometry of the reaction. You can develop the heat of combustion, which can be approximated as a constant or a property, a combustion property of the polymer or the material. But then you will need to know the burning rate. How many kilos per second, how many grams per second are burning, and then when these grams are burning, they will release that amount of heat, mediated by the heat of combustion. But the amount of the burning rate, which is how many grams per second are burning, actually you can express it as the burning rate per unit area times the area. And it's a very nice, a very elegant way of splitting the size of the fire. Visually, you're looking at it, the area of the fire that is burning, and then down to two variables that can be considered material properties. The heat of combustion obviously depends within a range, because depending on different conditions, the heat of combustion might be not complete, it might be incomplete, but the heat of combustion gives you an order of magnitude of material property. The burning rate per unit area happens to also be a material property or a pseudo-material property, because when you have a flame over a solid, the amount of heat that arrives to it is very similar, and actually the way the material responds, the heat transfer is all the same, so all that can be cast in a different pseudo-material property, which is the burning rate per unit area. And then the area of the fire is whatever the area of the fire is. That's the history of the fire. It started small, and it started to spread horizontally, vertically, a fraction, horizontally, a circle, a line. That's depending on the scenario. But it's a very useful equation to relate the size of the fire in terms of heat through the area of the fire and two material properties. Okay, so this is what I do here. I just highlight that the heat of combustion could be considered a constant, and the burning rate per unit area can be considered a constant. Okay, and it's all about then about the area. You can go into different books. This is another table from Quinteri. These are different materials, some of them liquids, some of them solids, and they give you here the typical burning rate, which is called the asymptotic burning rate. Okay. The burning rate per unit area. So for a fuel that has, obviously if it has more area and all of the areas receiving an increasing amount of energy, then you will have a different fire. But per unit area is, the asymptotic value is the heat that the flame is able to release, its own flame, not the flame of somebody else, its own flame, divided by the heat of pyrolysis. Okay? That ratio gives you also an order of magnitude of how much fuel will this fuel release when it's actually burning from its own flame. And this is tabulated. For example, you can see which one has a high value. Liquids have a high value. Okay, they actually release a lot of fuel into the gas phase that will fit into the flame for the same amount, for the same fire conditions, because they will develop a flame that is able to do that. Or which one has a low value is polyvinyl. Okay, in general form. Has a 16. That's another very exciting one. Polyethylene foam over here has a relatively low value, I have to say. okay, which is the amount of fuel. Because taking into account polyethylene foam, it's mostly air. It's literally 95% is actually air. There is very little fuel into it. So the amount, although it ignites really quickly, there is very little fuel that actually can be released. But then polyethylene foam itself is not the fire that you worry about, is that the polyethylene foam will actually start to ignite other things around, and they will drive the fire in a different way. So this is a table that you're familiar with, so to speak. This is a table that gives you the heat of combustion. Okay, so we're just going through the tables where you can actually identify the fuel that is burning, and you can put this into the heat release rate equation, heat of combustion and burning rate, and then that gives you something to do with the heat release rate of the fire, which we're going to look at later on. Okay, so you have ignited, the fuel has ignited, has developed a flame, and you know now that the flame will have specific shapes. We have seen this already in the class. In particular, flames on Earth are vertical. They prefer the vertical because of buoyancy. The hot gases develop a force that goes upwards. Also, there is a stream when the flame is bigger than a significant size, not just a candle, but it actually becomes turbulent. The candle is just laminar. But if fires in space can still happen if there is oxygen, but they have no preferential direction. The turbulence that is developed makes flames to have three regions, and the three of them are significantly different in the sense of the dynamics or what it will be encountered, because there could be a permanent flame, there is an intermittent flame over here, and then there is a plume. When the flame stops being a flame, literally, but those molecules that are still warm are moving, that is actually the plume or the smoke, if you want. And in fire, the plume is as important almost as the flame itself. Take into account that actually what kills people in reality is the smoke, not the fire, not the flame itself. But the flame is actually what producing the smoke and driving it all around the building. So in fire science, smoke dynamics are as important as well as fire dynamics. We just mean fire because there is no fire without a smoke. Depending if it is important, because if another fuel finds the flame in the permanent zone or in the intermittent zone or in the smoke layer, the ignition source of this fuel will be different, or there is a piece of a structure, a concrete beam or a timber beam that is actually finding the permanent or the intermittent or the smoke, it will be challenged by the fire in a completely different way. So this is structure, and the length of the flame is important to understand, because when you look into effective temperatures of this region, and this is something that we have already seen, this is a very famous plot. This is the excess temperature from the ambient at different locations of the flame, and this is a non-dimensional variable that gives you distance from the base of the flame. Okay, this is going upwards. It's non-dimensional. It takes into account the heat release rate. This is what we call the permanent flame. This is the intermittent flame, and this is the plume. And you have a continuous, okay, not a smooth, but continuous curve that takes from the highest temperatures are in the permanent region, and they drop to the intermittent, and they further drop in the plume. Okay, and that is obviously, you can imagine that is not the same. Having the next fuel that is going to ignite, crossing and being in contact with this fire by the plume, where it's actually below 200 Celsius, which will actually not ignite. It will just be degrading and maybe melt and paralyze a little bit, but it will ignite, as opposed to actually finding the intermediate region, which has an average temperature of 500 Celsius. It will ignite. Definitely will ignite. Actually, it will ignite quite quickly, or actually if it actually is exposed to the permanent side of the flame. Okay. As I said before, smoke is very important. We actually, in fire science, we develop a significant amount of our time into looking into the plume itself. And the plume is this beautiful, so to speak, fluid mechanics phenomena. So the fire is below, not forget, but for the side, it's not about combustion, it's just about heat. This plume is carrying heat, it's hot, it's moving upwards vertically because of flammability, and it's a boundary layer. That's what it is, it's a plume. It's outside the plume, there is quiescent air that is cold, and the plume itself is just carrying the heat, and as it moves upwards, it's spreading its momentum and its energy laterally, and then the plume grows, so it has a V shape. The plume is smaller at the base and is bigger at the top, but it's more intense at the base and is less intense at the top, because as it spreads the momentum and the energy, it starts to lose momentum and energy, and there is a point where the plume is very weak and relatively cold, and actually it stops existing. But close to the flame, it actually is a very strong jet, but it's small in size. And there are beautiful analytical theories that allows you to understand this boundary layer and allows you to actually design how to handle the smoke of a fire in a building. Because remember, smoke is what kills people in case a fire happens. And you obviously always try to trap the smoke in the higher parts of your building because you know that's where the smoke will go. You don't try to catch or deal with the smoke in a building at the ceiling, at the floor, because that will be, you should definitely be fire. This is just the type of correlations that we use, very nice. They come from fundamental pioneering experiments, have been validated. If you want something fancier for different conditions that are not these canonical situations, then you have computational fluid mechanics or actually further experiments. This is the temperature in the center line of the plume as a function of the height. And you see it has this decay power with the 2 to the 5th, 2 to the 5th to the 5th thirds, actually, with the heat release rate, and they go downwards. So obviously the center line at 25 meters, it actually is just 50 degrees. It actually is about to be stopped being called a plume. It's just a flow. Whereas very close to the source, maybe just 5 meters, the temperatures are significant. This is just about the smoke layer, smoke movement, smoke dynamics, nothing to do with combustion itself, but combustion was the origin of the smoke. So perfect. So now we have talked about how the heat is released in the flame and actually how it develops a plume. And we can start seeing what happens with the spread. So you have a fuel layer, you have ignition, there is a flame that establishes itself, and that's what happens is there is a continuous movement of this flame forward because heat, a fraction of the heat from this flame, is heating the next layer and the next layer and next layer. What you have is the process of growth by the specific form of flame spread, which happens to be an absolutely fascinating phenomenon. It's just not the ignition and the flame spread. Flame spread can be thought, as I said already, as a succession of ignition events. So if you do that, and S is the speed of the flame, how you have a flame that is developing. If you look at the leading edge, the velocity of this leading edge is actually the flame spread velocity. Nothing to do in orders of magnitude or the reason why it's burning to the flame speed of a premix flame. Okay, a premix flame is really fast. Remember, for methane, it's in the order of 30 centimeters per second. It's really fast. These flames in a solid are much slower. We're talking about 30 centimeters per minute or something like this. Okay, you have probably played with this yourself when you are playing with this competition of you have a match and who can hold the match burning for longer. Have you played this game? Raise your hand. No. Still is a lot of fun. Anyway, so you have a match. You know that there are competitions and there are ways of winning this competition, how you can actually hold the flame for longer. So this is actually an experiment that you can understand in terms of the flame speed, the flame spread rate, S. It is the area that is covered by the flame divided by the time to ignition. The time to ignition that we saw before, that actually is a beautiful theory. This is thick or is thin. The stick of the flame of the match is actually a thin one, so you could actually apply this to a match by using the thermally thin one. And this is a parameter that depends on how you're holding the flame. If you're holding the flame upwards, okay, the heat will only cover that the next layer will ignite a very small amount of material. Therefore, your flame speed will be lower for the same time to ignition. But if you hold it downwards, what happens is that the flame actually covers all this material, and all this becomes the next layer that is going to be heated up by the flame, and actually you have about 3 to 4 times faster flame speed. Okay, so and whoever wins this competition of holding the match for the longest will keep it upwards, and then they will do the little detail of, if you are interested, you have to move the flame a little bit to allow the turbulence and the alternation of heat transfer to take place. Good. Okay, so if it's thin or if it's thick, you can actually bring this into the flame, and then you just look into the arrangement. But it's not just about vertical and horizontal. What about something in between? So this is a video that I'm going to show you. These are pieces of thin wood, plywood, very thin. We hold it, we anchor in one location. This is where the arrangement is here, and we ignite on the other end. So this one, for example, we ignite, and the flame will go downwards, about 15 degrees downwards. This one will be flat, literally 0 degrees of inclination. This one over here is 90 degrees inclination. So we literally ignite at the bottom and it goes upwards. And this one is 15 degrees going upward. Okay, so I'm going to show you now. It's a video dynamite is synchronized. So ignition always happens at the same time. And you can see in real time the 4 flames racing. Which one is going to burn completely first? 90 degrees, right? So that's why you don't hold the match like this. You hold the match like this. So which one, and what about the other ones? Which of these 3 is going to be fastest? Flat, gently downwards, gently upwards. Which one is the fastest of the 3? Which one? 15 degrees, yeah, this one. And of these 2, which one is the slowest? So this one is the slowest. Why? Why is this one slower than this one? So your intuition is correct. Why? Say again?
Gravity.
Yep. But you didn't finish. So gravity does what?
So it pushes the flames upwards, but it actually has to go.
Perfect. Exactly. So the flame will always be upwards, no matter what is the inclination of the fuel. The flame will not see the inclination of the fuel, but then it will have to transmit heat by convection and radiation to the next layer. And if you incline it away, the radiation that falls on it is lower than if you incline it closer to it. So that's why this one is significantly lower than this one. So this is an experiment. I'm going to show you the video. I think it's going to work. Yeah, good. Yeah, perfect. This one is really ridiculously fast. This is in real time. Okay. This one is fast. This one is taking too long, a little bit boring, and this one is just glacial. Okay. So it's literally what we said before. We put this all together. This is inclination here, angles of inclination. This is the fuel you ignite and it's going downwards, and this is going upwards. And you can see how there is a gentle decrease of speed of burning, the spread rate. Gentle. There is always going down, but very little. Whereas in the upward, it accelerates very fast. Okay, and the fastest is if it's 90 degrees. And then this will be, if you continue going higher, then it's like you swap this symmetric, okay? And then you can actually go all around the clock and you will get this plot. Good. So now you can actually put all this together and come out with an approximation to a flame spread rate of a fire. So if you have a fuel, you are looking at the fuel from the top and it ignites in the center, okay? At some point, the fire is, if it doesn't have a preferential direction, because it's not going upwards, or because all the fuel is uniform, okay, then it will be circular, because the flame spread will be uniform direction. And actually, the flame spread, if the fire, after the fire has grown a little bit, the flame spread will be relatively constant. Then the radius of the area that is burning, all these areas burning, the derivative will be the spread rate. S, which is a constant. If it's a constant, then the radius will be a linear function of time. The radius will increase linearly with the spread rate. And then if the radius is linear, the area of the fire becomes quadratic. So the area of your fire, when you have constant uniform spread rate, it actually means that the area of your fire is pi st to the square, with s being a constant. So you can bring now the area into the equation that we had before of the heat release rate, where we have a pseudo-constant material property, another pseudo-constant material property, and now we bring the area, which actually means S, the spread rate, is also a pseudo-material property, and then all these are constants, a mathematical constant, physical constants, and then you just have the heat release rate in these conditions will grow, the heat release rate will grow quadratically with time. And this is something that has been seen very often. It can all be boiled down to a constant where the heat release rate grows in time. This is a law of growth with a constant here. It's a constant that depends on the heat of combustion, the burning rate, and the spread rate, but actually grows with the square, and this is important. It actually is tabulated, and different conditions, it can give you to a slow fire where you have a very small alpha, or it can give you a medium, a fast, or an ultra-fast fire where it gives you a massively large alpha. When you plot them all together, what you have is time and heat release rate, and it gives you a law for the growth. And when it's low, you have a lot of time to react, a lot of time for people to evacuate, a lot of time to detect still not been too late for the firefighters to react. But actually, when you become medium or ultra fast, then the situation aggravates, and you might be losing this race between the evacuation, blue curve, and the fire, red curve. And in particular, ultra fast is considered to be actually in a suicidal scenario. Only happens in reality in industrial facilities, but it's a very scary scenario, and the slow one is what everybody desires, right? So when we engineers literally design the built environment, we ask everybody involved in the building, clients, residents, owners, government, please don't have a fire. But if you're going to have a fire, make it slow. Do not alter the flame spread. Do not alter the heat of combustion. Do not alter the burning rate such that you start having an ultra-fast fire, because then it's not just that you have a flammable environment, it's that you are going to die, you and the people with you. Whereas here, we have a chance to get you out alive, and we might have a chance to stop it before the damage, economic damage, or the consequences are too large, okay? Which is already a risk approach. Which is saying, this layer, when you are designing at this layer, you are trying to make the fire slow, you are already assuming prevention has failed. And then you obviously, with the other hand, you're designing your detection and your evacuation and your suppression, okay? And the compartmentation. But you are hoping really that the fire will be slow. Not hoping. You can actually help. You, for example, can say, as it happens in the UK, sofas, for example, in the UK, and mattresses, which are very scary elements in residential places. In the UK, they have to pass a specific standard of flammability. Literally, they take the sofa. IKEA does this very often. We came out with a new sofa. We love it. It's super amazing and very cheap. Really, put it into a test, and you have to show that the materials of what is made, it will ignite for sure. Okay? But it will ignite taking too long. When it burns, actually the amount of fuel, the burning rate is low, and the split rate is small. And you actually do that by either playing with the amount of materials or by retarding the materials, which is this magic chemistry. It's literally magic chemistry. Okay? They put these really strong chemists with very complex chemistry, but just tiny little amounts in your polymer matrix, and then the resulting behavior in fire is lower spread rate and lower heat of combustion and lower burning rate. And then it passes the test, and then IKEA can sell in the UK. Other countries, like France, have no requirements of flammability. You can come out with whatever you want, and you could sell it legally in France. Obviously, what happens in France is that they get a lot of sofas from the rest of the world. So in France, they have a lot of inbuilt redundancy, so to speak, just because they share market with other places. But they themselves don't have a requirement for this. In the US, as we speak, they used to be more like the UK. In California, for example, they were very strict on the flammability of sofas that were sold, and the Americans were very happy with this. But actually now, about 3 years ago, they have removed this and actually have gone from the UK system to the French system. And as we speak, this is actually happening in the United States. So everybody is looking at, it's like an experiment with real people without telling the people, which is illegal, by the way. They are looking at the fire statistics, literally as we speak, to see if there's an increase or it stays flat. So they did this regulation change with the hypothesis that the fire statistics were going to remain the same or continue the historical downward. It's an hypothesis. If suddenly the statistics, especially, I mean, whatever happens in California happens in the whole of the United States in terms of sofas, if the actual statistics start to go up, okay, against the natural tendency for a significant amount of time, there is a big possibility that the experiment had the wrong hypothesis, okay? And that's very scary, at least from my point of view. Something to note is that it's not only about flame spread, but the first point of the fuel that ignited, which was this one, has been burning now for a while, actually has been burning for a while, actually is running out of fuel. At some point, it will stop burning. It actually is what is called the trailing edge of the flame. This is the leading edge, this is the trailing edge, and it's burnout. This will stop burning because it has been burning already for enough time. When you look into the time to burnout, which is you take the heat of combustion, you take the amount of fuel that you have, and you take the burning, you take the amount of fuel that you have, this is the height, the height of the fuel and the density that you have and the burning rate of the fuel. You do this for a different amounts of fuels that we have in the room, different materials, different thicknesses, you get this magic number, which is about 15 minutes. In reality, it goes from 12 to 19 minutes. So when 21st century Earth, okay, in particular Western civilization, when something burns, the flame can stay in that single position for about 12 to 19 minutes. It cannot stay for longer. The fire will later on will be in a different place. Okay. And this explains things like this. This is not just a slab of material. This is the next level of experiment. This is not just little slabs that we do in the lab. In particular, in our lab here in Imperial College, it's a small lab because it's South Kensington. So we burn a lot of small things. But no, in reality, what we do is we develop a science that we want to be able to help other people trying to understand how bigger things burn. But you can actually burn a sofa. So this is an experiment that was done in the United States where they put different sofas, they ignite in different locations, and they measure the heat release rate. And what you see is, you see a quadratic growth of the fire. This is pseudo-quadratic. It's controlled by flame spread under pseudo-constant conditions, okay, but growing in area. It reaches a peak. That's the worst moment. Okay, the fire has spread in many locations, and then it starts to decay. Why does it start to decay? The fire is still burning for actually several minutes. But why does it reach a peak and then it goes down? I've told you, it's going up because of flame spread. But then what does it come down? Burnout. The first location where you ignite it, in particular where the arsonists put the ignition, actually at some point it stops burning, and then the next one that was burning starts burning, and then actually there's a point where the trailing edge is faster than the leading edge, and actually that means there is less surface area, right? Now you have, instead of a circle, you have an annulus, and the region of the annulus is decreasing, and that means you end up having a smaller fire, okay? And then you have a residual phase, this one over here, which all the very complex different materials. Now it's not just burning the foam of the sofa, now what it's burning is the frame, which could actually be made of wood, which has a completely different structure, and then you have this kind of a melee of a fire, okay? So this is the beginning of the sofa. This actually reaches the peak. In this particular case, it's 3 megawatts when the sofa is burning. You don't want to have 3 megawatts of heat in your living room. It's not pretty, it's not good, it's absolutely catastrophic, and actually it has all the smoke spraying through the house, okay? And when the long phase, where the sofa is burning for a significant amount, when it's free burning, is half a megawatt. Good. So now something important. The experiment that I showed you before is an experiment that was done in the open. In reality, it was inside a lab, but the lab was really large, and it had an extraction hood. So actually, the plume was immediately taken away from the environment, and it was dumped somewhere else. But what happens if we do this in an enclosure with a ceiling in particular? The walls as well, but the ceiling. So there's this famous experiment, is that these two curves, where exactly the same slab of material was burned in the open, it's a small slab, or with a ceiling on top. And this one over here is when it's burning in the open, and this massive transition over here is when it happens when you have a ceiling on top. So just because you have a ceiling, and see this, just because you have a ceiling and the flame impinges on the ceiling, it actually has to travel horizontally instead of vertical and actually find a way out. It completely modifies the burning behavior. Why? Well, it might be written somewhere there. This is a small scale experiment, and even at the smallest scale you see this massive alternation of the fire dynamics just because you have a ceiling. Why would the presence of a ceiling modify how something is burning at the bottom? Or the heat gains. So what happens is now the flame, instead of going conically away, okay, every single location of the flame is releasing heat. So some of these sources, some of the burning sites are very far away from the fuel that actually is paralyzing. Some of them are very close. But when you have a ceiling, you force the flame to grow laterally, horizontally, you are netly increasing the amount of radiation that is actually, you're creating a surface that before could not reach by radiation the fuel, but now actually can reach the fuel. So you significantly increase the amount of radiation from the flame to the fuel. But not only that, the smoke, which used to be vertical and actually could hardly radiate anything because of lower temperature, but also because the view factor is very low, now even the smoke starts to radiate because actually it can accumulate on the ceiling. And the ceiling itself starts to heat up, and it's a black body, and it's a really high temperature, and it actually itself starts to radiate. So everybody starts to radiate, and all the heat that would have lost to the environment in the free burning actually is radiating back to the field. You have a significant increase, not just a gentle or substantial, but a significant to very large increase of the burning rate, just because there is an enclosure. Which is kind of like this scenario that we have, where you have this smoke layer, okay, which means that these flames and this smoke and the ceiling itself is radiating to everyone that is in the room, not just the location that is burning. It also creates what is called the smoke layer. I referred to this below. Okay, there is literally now a zone going across the compartment that is all smoke. Okay, and it likes to be above because it's buoyant. It's being trapped by the ceiling, but it wanted to go upwards. Okay, and then you have a bottom layer that is air, and the two of them are connected through a pump, which is the fire. And the fire is entraining air, because this plume, fluid mechanics-wise, will entrain by transferring momentum the air, so this air will be going into the plume. And also this air will be called by the flame to combine with the hydrocarbon and burn. Okay. So there are two reasons why the air of the air layer is going into the pump and being converted into smoke and changing to the other layer. So two layers, smoke layer and the air layer. Humans can live in the smoke layer. Humans will die in the smoke layer. The smoke layer starts to grow and it starts to descend as the fire grows in size and continues burning. Okay? And people, that's why in case of a fire, you are late in the evacuation, you should crawl, because you should put your head, the breathing of your body, as far as possible from the smoke. If you inhale smoke, just a little bit of smoke, you will very quickly become incapacitated. You don't die. You become incapacitated, and then you fall, and you literally cannot evacuate anymore, and you will have to be rescued by someone. And then is when you might actually die, because of the flames can actually seriously do harm. Okay. Then the descent of the smoke layer will modify the dynamics, because either we'll find a window or a door, and then the smoke will actually leave the compartment through that, and then there will have to be a balance between how much is being pumped of smoke into the room by the fire and how much is leaving because of the windows and the doors. This window might actually be initially closed, but then the fire and its radiation might actually crack it and then break, and that will change the dynamics. And when you have a door or a window, new or old, you actually have the arrival of the oxygen through that. Okay? So in a compartment, there is a very important coupling between fluid mechanics and thermodynamics of the compartment, and the vents, windows or doors, have a very important role to play. Okay? There is a theory, a beautiful theory, that tells you what happens not just to the smoke. There's not a plume. When the plume touches the ceiling and bends laterally, it's become what is called a ceiling jet. It is the same phenomena, but now has been forced to use that buoyancy and that momentum to go horizontally. It doesn't grow any farther because of height. It just continues horizontally. It's a ceiling jet. There are these beautiful analytical theories that tells you the temperature of the ceiling jet as a function of the heat release rate and a function of the height, and even the velocities inside the ceiling jet. And these, for example, engineers use them to see where to put the sprinkler. So this is the fuel. Where do I put the sprinkler? Obviously, you want to put it here, right? But what if you don't know where the fire is going to be? So what is the farthest fire that the sprinkler can be activated by? So as you put the sprinkler farther and farther and farther, you can see by this law that the temperature starts to drop. And the sprinkler has a critical temperature for activation. If it's too far away from the fire, if it's over here and it's too far, it might never be ignited. Sorry, not ignited. It might never be activated by the fire. Obviously, if it's right above, hopefully it will be. But the spacing of the sprinklers is critical of that. Is that it has to be activated and still be within reach of the fire that is trying to suppress. And then we continue in the evolution of this fire, and we reach the flashover, okay? Which is something that comes with 3 symptoms, not 3 definitions, 3 symptoms. I'm going to show you to you now. One of them is what is called external flaming. So if you are looking at the fire from the outside, this is an experiment where the burning is happening inside. It's how we do in the lab compartments. It's a box with one slot. That's the window or the door, okay? They have fascinating experiments anyway, no matter that they're smaller in size. The fire is happening inside. How do you know? Because you can see the smoke layer actually venting out through the top part of the vent. The lower part, the air is coming in. You don't see it, but you can see the smoke coming out. Okay, so this is the exchange of momentum and energy between the exterior and the compartment. When you reach flashover, which is the largest fire that can happen within a compartment, Italy will not be able to grow any farther. The fire runs out of oxygen. The amount of oxygen that is going through the bottom part of the vent is not enough to sustain the combustion process inside. And actually what it does is the excess fuel that has been paralyzed, but it doesn't have enough oxygen, leaves the compartment to find oxygen. And then you have the phenomenon of external vent. It's called external flaming, which is you see flames coming out of the compartment. That is a sign of flashover. When you see a compartment, windows, you see a building, the windows are not just coming out of the smoke, you see the flames coming out. Okay, now when you see a fire in the TV, you can see that it's indicative that the fire in that compartment has reached its maximum size. That's pretty bad already, okay, when flames are coming through windows or doors. And this is just one of the indicators or signs. There are two more that can be defined to look into flashover, is when the average temperature inside the compartment, when you average the whole temperature of this compartment, you are talking about an average is around 500 Celsius. That is insane. Insanely big fire has to happen in this room to have all this volume average around 500 when you know that the typical maximum temperature of the diffusion flame is in the order of 1,600 when it's diffusion flame turbulent. Okay? Or that the heat flux that arrives to the lowest heat flux, which is always the heat flux arriving to the floor, okay, the highest will be that arrives to the ceiling, when the lowest heat flux that is arriving to the room is in the order 20. At 20 kilowatts per meter square, any polymer will ignite. Any. It's just a matter of when. And probably some of them will ignite extremely fast, within milliseconds. Some of them might take actually a few seconds. Okay? So these three definitions, you see external flaming because it has run out of oxygen. The lowest heat flux in the compartment is insanely high, or actually the average temperature in the compartment is pretty much the average temperature of an intermediate flame, the whole of the compartment. These are indications of the fire has reached its maximum size. Okay? When you plot this together, this is time in the horizontal axis, this is the heat release rate, and this red curve is ignition. The fire grows quadratically, and it reaches flashover. It has a really fast growth, okay? And then it reaches its maximum, and it actually will not change its maximum unless you change the vents. So when it's burning flashover, the heat release rate will remain the same inside the compartment, not outside, inside the compartment, unless you open doors. You open doors, you open windows, the fire will grow because you have actually more ingress of oxygen. Or if you close, it will actually shrink, okay? And then it will have burnout, where it will run out of oxygen. Or if actually the sprinkler activates on time, then you might actually have a fire that is growing, but then the sprinkler activates and then the fire actually itself goes down. So obviously this is what the firefighters will love, fires that are controlled by the sprinkler or by the conditions of the compartmentation, such that when they arrive, the fire is small and going slower. As opposed to the scenario that they fear the most, is when they arrive, the fire has reached its maximum size, and if they don't do anything, it actually could remain at the maximum size for a significant amount of time as the smoke is spreading through the compartment and through the building and through the maze of the system. Okay? Good. So that's it. That was my introduction to fire dynamics for you. Okay? Now, it's the last lecture of the year. So at this point, you will be having burning hot questions about the exam. So I've told you already, I think, that it will be two parts, theory part and the numerical part. If you go to exams in the past, it has been the same, and I remain loyal to that type of behavior, okay? When you look into the theory questions, I could ask theory about anything that has been covered theoretically in the course, okay? There are many things. For example, I might ask you to explain briefly or longly. I will be explicit, and you will see that the marks that I assign to this question are proportional to what I'm asking to you. If I say, sometimes I give you a budget. I say 100 words. I mean, I'm not expecting you to count 100 words exactly. You are not a machine. But in the order of 100 words, okay? Which is not 500, and it's not 5. All right? It's order of magnitude. We're engineers. Sometimes I say brief. Sometimes I say sketch. If I say sketch, you know my now. You know me. I'm expecting you to sketch. So if I ask you to sketch and you don't sketch, I cannot find any excuse, no matter how good I feel that day, to give you partial marks because you didn't sketch anything. Now, if you sketch something that is not very good quality, not complete, then it's the art of marking. It's how do I feel about this incomplete sketch? Obviously not full marking, but it has the most interesting bits. I can see something. But if you don't sketch, I cannot give you not even partial markings, okay? Some topics that I might ask you about, these are just some examples very quickly when I went through the slides. I could ask you about fuel types, stoichiometry, equivalence ratio, premix diffusion flames, quenching, Brooks-Schumann, D-squared law, emissions, combustion engines. Sorry, the last one over here is smoldering combustion. Is because in the past this course, instead of introduction to fire dynamics, it had an introduction on smoldering combustion, but you don't have that, okay? I will not be asking about you about the smoldering combustion. Okay. So all these topics, all of them have been mentioned in the class, are in the slides, are in the book, except the specific topics of diffusion and turbulent flames and particle combustion, which are covered, and some pollutants, which are covered in the notes of the slides. Okay? Good. So that's my last lecture. I will still see you around in the hallways, in the exam maybe, and also hopefully when you graduate, I'm still here. I'm not going far. Okay, but it has been great to teach you combustion, and I wish you the best in your careers.